Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. For this question, a student has asked me to find all the solutions of the modulus of e to the 2I theta minus 1 equals root 3, where theta is between negative pi and pi. And I should note that this question actually comes from the 2020 sample exam that NESA released for Extension 2 Math, and in particular it's question 12C. Now that sample exam actually does provide suggested answers, but for this particular question the suggested solution takes a geometric approach, and I gotta say it's not a particularly intuitive method, and I suspect the student who sent this through was kind of having a bit of trouble understanding that sample solution. So what I'm going to do is I'm going to tackle this question using algebraic methods, because I think they're actually a lot easier to follow. They may not, the approach I'm going to use might not jump out at you as being obvious, but hopefully once you see me work through it, it makes enough sense that you could possibly replicate it if you had to. So I'll just write up this question. So we want to solve this equation where we've got the modulus of e to the 2I theta minus 1 is equal to root 3, and this is for theta between negative pi and pi inclusive. So kind of at first glance what we're dealing with, it kind of looks like the kind of Euler's form kind of looks like it could be helpful, but it's just kind of not in the perfect format. But I think the first step we can do, and again this might not be obvious to do, but when you see me do this you're going to kind of realize where I'm getting to. I think we can factor out an e to the I theta from here. So we'll kind of write this as e to the I theta bracket. Now here we've got e to the 2I theta, so we've got two of these, so I'll get e to the I theta as the first factor. And then if I want to get 1 here, I need to subtract 1 on e to the I theta. So that's essentially equivalent, so that's still going to be equal to root 3. Now I'll write this as e to the I theta bracket e to the I theta minus e to the negative I theta. So that's just bringing this power in the denominator up and making it negative. So that's still equal to root 3. And what I might do is I'll just do a little side step here where we focus on what this bit here is, because it might not jump out at you, but this is actually a complex number minus its conjugate. And the way I can flesh that out, let's just let some complex number z equal cos theta plus I sine theta. So that kind of basic mod arg form of a complex number where the modulus is just 1. So this kind of sits on a unit circle. And we know we can also write that in Euler's form, which is e to the I theta. Now if we think about what would z bar be, well, z bar would be cos theta minus I sine theta. And if I think about cos and sine, and particularly cos being even and sine not being even, we could write that as cos negative theta plus I sine negative theta. And the reason we can do that is because we know that cos of negative x equals cos x, it's even. And sine of negative x equals negative sine x. So these are effectively equivalent. And so you can kind of see that putting that in Euler's form, you get e to the, well, we've got negative theta here, so it would be negative I theta. And so that's how you can see that, therefore we can say that e to the I theta minus e to the negative I theta, that's effectively, we could write that as z minus z bar in this kind of by this definition of what we've defined z. And if I kind of stick with my mod arg form, we could write that as cos theta plus I sine theta minus cos theta minus I sine theta. And if I just kind of simplify this, so we get cos theta plus I sine theta minus cos theta plus I sine theta. So the cos thetas disappear, so we end up with 2I sine theta. So what I'll do is I'll take that and substitute it in. So therefore what we end up with is the modulus of e to the I theta times 2I sine theta being equal to the square root of 3. Now, if I'm taking the modulus of things being multiplied, I can multiply the moduluses. So that means we can get the modulus of e to the I theta times the modulus of 2I times the modulus of sine theta equals root 3. And here we can kind of go back to basics, and this e to the I theta, which is just another way of writing cos theta plus I sine theta, this is in mod arg form where the argument is 1. So we know the argument of e to the I theta is just, the modulus. It's in mod arg form where the modulus is 1, and the argument is theta. So the modulus of e to the I theta would be 1 times the modulus of 2I. The kind of magnitude of that is it's just going up by 2, so that modulus is just 2, and then we're just left with the modulus of sine theta. So that's still root 3. So we can kind of say that the modulus of sine theta is equal to root 3 on 2. And now, hopefully, this result, if we're thinking of sine theta being equal to root 3 on 2, hopefully that's quite familiar. Now, I'll just turn over, because we're still dealing with the modulus of sine theta. So if we kind of think of that in terms of absolute value, it might help you to think of that as the square root of sine theta squared is effectively the absolute value of the modulus. So that's going to be equal to root 3 on 2. So if I square both sides, I'd get sine theta squared equals 3 on 4. But now to get just back to sine theta by itself, I take the square root of both sides, and we end up with the plus or minus root 3 on 2. And you could jump straight there from the modulus, but I think perhaps it just helps to walk through the steps we've taken algebraically to be very clear that we're looking at both the positive and negative solutions. So if we look at those one at a time, so we're looking at when is sine theta equal to plus root 3 on 2. Well, I might just get my ruler and draw up a kind of quadrant, and we can kind of just map out. I'll just do a rough sketch. Maybe I'll just use a different color, but we can kind of know from our basic triangles that if you go, it's a 90-degree triangle, and you go 60, 30, you'd then go 1, 2, root 3. Hopefully that's a common triangle you've committed to memory. So if we look at the sine of 60, opposite over hypotenuse, we can see that sine theta would equal to root 3 on 2. So that would give us theta equals 60 degrees. That's one solution, but we could also see if we draw the equivalent triangle coming into this second quadrant. So it's still 90 degrees, so we'll have 60, 30. So here it's -1, and then root 3 and 2 still. So the sine of this is root 3 on 2, but if we're measuring our angle from quadrant 1, we're actually going 120 degrees. That's kind of how we measure that angle. So we'll also get theta is 60 or 120 degrees. Both of those will give us root 3 on 2. So what's that? That's going to be pi on 3 or 2 pi on 3. So that's going to give us our positives. Now if we look at sine theta equals negative root 3 on 2, we can just draw them in the negative quadrants. So I'll just use red here. Same kind of idea, but now we're going negative 3 and 2, and it's still 60, 90 there, and 30. And same deal here, we can draw this triangle 90 degrees, 60, 30, negative root 3 and 2, and we've already got our negative 1 there. So we can see that if we come 60 from the opposite direction, we'll get the sign of that would be negative root 3 on 2. So we can say theta is equal to, if we're coming in the other direction, we just call that negative 60 degrees. And then the same deal, if we come all the way further, we end up with 120 degrees. And that's also going to give us negative root 3 on 2. So that's effectively negative pi on 3 or negative 2 pi on 3. So therefore we can conclude that the solutions to what we were working on, this equation here, in this domain, there's 4 solutions. Theta will be plus or minus pi on 3 or plus or minus 2 pi on 3. Boom! So there you have it. That's an algebraic way of working through this question. Naturally, there are other ways. As I mentioned, one of those ways you can think of it geometrically, and you can kind of think of a unit circle in the Argand plane, and also a circle of radius root 3 center 1, and look at where they intersect, and you'll get to the same place, but I just don't know if that's intuitively a way that most people are going to go to, and it seems like a kind of an interesting method, but an odd method, whereas I think this algebraic approach is probably much more simpler to follow along with, and you kind of need to make use of a few results that hopefully you're familiar with as you work through the complex number topics in Extension 2. So hopefully you're eventually quite comfortable with these ideas of jumping between Modarg form and Euler's form. And really, I think a lot of the creativity with this approach just came right at the beginning, where you thought to factor out e to the I theta and kind of end up with this, what's effectively z minus z bar, that you can then simplify. So yeah, hopefully you found that explanation helpful. If you did find it helpful, please be sure to give the video a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.